banks and insurance companies are increasingly using computer-assisted or fully automatic computer-based link analysis for fraud detection, telecommunication operators for telecommunication network analysis, the medical sector for epidemiology and pharmacology, law enforcement investigations, search engines for relevance rating, and conversely, spammers for spamdexing and business owners for search engine optimization. And everywhere else where relevance is important. Similarities in time behavior in both nodes are also used to form links. Climate networks are an example, where the connections between two locations are determined, for example, by the similarity of rainfall or temperature swings in both locations. Link-based centrality measures are used by several web search ranking algorithms, including Google's PageRank, Klein-Berg's algorithm, the Jacobian, and TrustRank algorithms. In information science and communication research, link analysis is used to comprehend and extract information from the structure of collections of web pages. The analysis could be of the interlinking between politicians' websites or blogs, for example. Another application is for classifying pages based on the number of times they are mentioned on other pages. Measures of centrality. Centrality measures, which are frequently used in disciplines such as sociology, can provide information on the relative importance of nodes and edges in a graph. Eigenvector centrality, for example, employs the eigenvectors of the adjacency matrix corresponding to a network to identify nodes that are frequently visited. Degree centrality, proximity centrality, between a centrality, eigenvector centrality, subgraph centrality. And Katz's centrality is all formalized metrics of centrality. The sort of centrality metric to be employed is usually determined by the goal or target of the analysis. If one is interested in network dynamics or network robustness to node/link removal, for example, the dynamical importance of a node is often the most relevant centrality measure. Mixing that is both assortative and disassortative. These notions are used to describe a network's, hub's connectivity preferences. Hubs are nodes with a significant number of connections. Some hubs prefer to connect to other hubs, whereas others prefer to connect to nodes with low connectivity rather than hubs. When a hub has a proclivity for connecting to other hubs, we call it assortative. A hub that is disassortative avoids connecting with other hubs. Hubs are said to be neutral if their connections have the anticipated random probabilities. Degree correlations can be quantified using one of three approaches. Networks of recurrence. The adjacency matrix of a directed and unweighted network can be compared to the recurrence matrix of a recurrence plot. This enables network measures to be used to analyze time series. From detecting regime shifts to characterizing dynamics to synchronization analysis, there are a variety of applications. Networks in space. In space, there exist many genuine networks. Transportation and other infrastructural networks, as well as brain neural networks, are examples. Several geographic network models have been developed. Spread. In a complex network, content can spread in one of two ways: conserved spread or non-conserved spread. The overall amount of content that enters a complicated network remains constant as it moves through inconserved spread. A pitcher with a set amount of water being poured into a series of funnels connected by tubes best represents the conserved spread model. The pitcher represents the source, while the water represents the content that is being disseminated. The nodes and connections between nodes are represented by the funnels and connecting tubing, respectively. The water disappears from the funnel that was previously exposed to the water as it goes from one funnel to the next. The volume of content changes as it enters and moves across a complicated network in the non-conserved spread. A continually running faucet going through a network of funnels connected by tubes best represents the non-conserved spread concept. The amount of water available from the source is limitless here. Additionally, any funnels that have been exposed to water continue to be exposed to the water as it goes through subsequent funnels. The non-conserved model is best for describing infectious disease transmission, brain stimulation, information and rumors, and so forth. Immunization in a network. The subject of how to effectively immunize scale-free networks that mimic reality networks like the Internet and social networks has been intensively researched. One such technique is to immunize the highest degree nodes, i.e., targeted because PCPC is relatively high in this scenario and fewer nodes need to be immunized. The global structure is not available in most practical networks, and the maximum degree nodes are unknown. Science of networks. Network science is an academic field that studies complex networks, such as telecommunication networks, computer networks, biological networks, cognitive and semantic networks, and social networks, with nodes representing distinct elements or actors and links representing the connections between them. Graph theory from mathematics, statistical mechanics from physics, data mining and information visualization from computer science, inferential modeling from statistics, and social structure from sociology are all used in this field. The study of network representations of physical, biological, and social phenomena, leading to predictive models of these phenomena, according to the National Research Council of the United States. History and backstory. The study of networks has emerged as a method of analyzing complex relational data in a variety of disciplines. The famous Seven Bridges of Ginsburg, written by Leonhard Euler in 1736, is the earliest known paper in this field. The foundation of graph theory, a branch of mathematics that studies the properties of pairwise relations in a network structure, was Euler's mathematical description of vertices and edges. The field of graph theory has progressed and now has applications in chemistry. In 1936, Danes King, a Hungarian mathematician and professor, published Theory of Finite and Infinite Graphs, the first book in graph theory, a sonogram of a first-grade class by Morneau. In the 1930s, a Gestalt psychologist named Jacob Morneau arrived in the United States. In April 1933, he developed the sociogram and presented it to the public at a medical scholars' convention. No one knew what the interpersonal structure of a group precisely looked like before the advent of sociometry, Morneau claimed. The sonogram was a visual representation of a group of elementary school students' social structure. Except for one boy who stated that he liked a single girl, the boys were friends of boys and the girls were friends of girls. The sentiment was not returned. The New York Times published this network representation of social structure because it was found to be so intriguing. The sonogram has a wide range of applications and has become a field of study in social network analysis. With Paul Erda and Alfred Pinion's 8 famous papers on random graphs, probabilistic theory in network science arose as an offshoot of graph theory. The exponential random graph model, also known as P, is a rotational framework for representing the probability space of a tie in a social network. A network probability matrix is an alternative approach to network probability structures that models the probability of edges occurring in a network based on the presence or absence of the edge in a sample of networks in the past. With the PANS model, David Hardtack and Kathleen Carley introduced the concept of a meta-network in 1998. All organizations are structured along with these 3 domains: individuals, tasks, and resources, they claim. Their paper introduced the idea of networks spanning multiple domains and being interconnected. Dynamic network analysis is a subdiscipline of network science that has grown out of this field. Other network science efforts have recently centered on mathematically describing various network typologies. Duncan Watts and Stephen Surgett described the small world network by reconciling empirical data on networks with mathematical representation. The scale-free network, developed by Albertina Barabas and Ria Albert, is a loosely defined network topology that contains hub vertices with many connections that grow in such a way that the number of connections versus all other nodes remains constant. The scale-free network model is a directed version of the earlier directed price model in the context of citation networks. There is significant debate among scientists about whether real-world networks are scale-free or not, with some claiming that they are common and others claiming that they are uncommon. Many in the network science community argue that knowing whether or not a degree distribution is fat-tailed is more important than knowing whether or not it meets the stricter scale-free criteria. Initiatives of the Department of Defense. In 1996, the United States military became interested in network-eccentric warfare as an operational concept based on network science. On December 1, 2003, Army Director for Research and Laboratory Management John Parliament proposed network science as a new Army research area to the Army's Board on Science and Technology. The BAST, the National Research Council's Division on Engineering and Physical Sciences, serves as a convening authority for discussion of science and technology issues important to the Army, as well as overseeing independent Army-related studies conducted by the national academies. The BAST conducted a study to see if identifying and funding a new field of basic research, network science, could help bridge the gap between what is needed to realize network-eccentric operations and the current primitive state of fundamental network knowledge. As a result, the BAST published the Network Science Study in 2005, which defined a new field of basic research in network science for the Army. Army basic research resources were redirected to start a new basic research program in network science based on the findings and recommendations of that study and the subsequent 2007 NRC report titled Strategy for an Army Center for Network Science, Technology, and Experimentation. Some of the key network science research efforts now underway in Army laboratories address mathematical models of network behavior to predict performance with network size, complexity, and environment, optimized human performance required for network-enabled warfare networking within ecosystems, and at the molecular level in cells to build a new theoretical foundation for complex networks. The Department of Defense assisted in the establishment of the first Network Science Center in collaboration with the United States Army at the United States Military Academy, which was started in 2004 by Frederick I. Moxley, with support from David S. Alberts. Cadets at West Point were taught the first interdisciplinary undergraduate courses in network science under the direction of Dr. Moxley and the USMA faculty. The USMA has also instituted a 5-course undergraduate minor in network science to better instill the tenets of network science among its cadre of future leaders. In 2006, the Army Research Laboratory, the UK Ministry of Defence, and a consortium of US and UK industries and universities formed the Network and Information Science International Technology, a collaborative partnership between the Army Research Laboratory, the UK Ministry of Defence, and a consortium of US and UK industries and universities. The alliance's goal is to conduct basic research in support of network-eccentric operations across both countries' needs. In 2009, the U.S. Army formed the Network Science CAT, a collaborative research alliance among the Army Research Laboratory, CETR, and a consortium of about 30 industrial R&D labs and universities in the U.S. The goal of the alliance is to develop a deep understanding of the underlying commonalities among intertwined social/cognitive, information and communications networks and, as a result, improve our ability to analyze, predict design, and influence complex systems, interweaving many kinds of networks. Subsequently, as a result of these efforts, the U.S. Department of Defense has sponsored numerous research projects that support network science. Network properties. Often, networks have certain attributes that can be calculated to analyze the properties and characteristics of the network. The behavior of these network properties often defines network models and can be used to analyze how certain models contrast to each other. Many of the definitions for other terms used in network science can be found in the glossary of graph theory. Average shortest path length. The average shortest path length is calculated by finding the shortest path between all pairs of nodes and taking the average overall paths of the length thereof, the length being the number of intermediate edges contained in the path, i.e., the distance du, v between the two vertices u, v. This shows us on average the number of steps it takes to get from one member of the network to another. The behavior of the expected average shortest path length, that is, the ensemble average of the average shortest path length as a function of the number of vertices and of a random network model, defines whether that model exhibits the small world effect. If it scales as O, special case of O is known as ultra-small world effect. Diameter of a network. As another means of measuring network graphs, we can define the diameter of a network as the longest of all the calculated shortest paths in a network. It is the shortest distance between the two most distant nodes in the network. In other words, once the shortest path length from every node to all other nodes is calculated, the diameter is the longest of all the calculated path lengths. The diameter is representative of the linear size of a network. If node ABCD is connected, going from AD, this would be the diameter. Clustering coefficient. The clustering coefficient is a measure of an all my friends know each other property. This is sometimes described as the friends of my friends are my friends. More precisely, the clustering coefficient of a node is the ratio of existing links connecting a node's neighbors to the maximum possible number of such links. The clustering coefficient for the entire network is the average of the clustering coefficients of all the nodes. A high clustering coefficient for a network is another indication of a small world, where ki the number of neighbors of the is the number of connections between these neighbors. The maximum possible number of connections between neighbors is, then, from a probabilistic standpoint, the expected local clustering coefficient is the likelihood of a link existing between two arbitrary neighbors of the same node. Disconnectedness. How a network is connected plays a large part in how networks are analyzed and interpreted. Networks are classified into 4 different categories. Clique/complete graph, a completely connected network, where all nodes are connected to every other node. These networks are symmetric in that all nodes have inlinks and outlinks from all others. Giant component, a single connected component that contains most of the nodes in the network. Weakly connected component, a collection of nodes in which there exists a path from any node to any other, ignoring the directional of the edges. Strongly connected component, a collection of nodes in which there exists a directed path from any node to any other.